Okay, so welcome back to another video. So here we have a geometry problem that we'd like to find the shaded area of. And in this picture, we have a square inscribed with a circle. And then also we actually have a line segment drawn from one side of the square to the other side that's tangent to the circle. And this actually forms this little, minuscule area that we would like to calculate. So just like any typical geometry problem that even especially the ones that I've covered in past videos, it relies a lot on, adding more things to the construction of our, given. And if we actually find areas of, a bigger region slash area of whatever construction we do add in, then subtract more to it so that eventually it actually forms, how exactly we want to find, our given area, just like so. You'll see where I'm coming from with this. So let's actually just jump right in. So we're actually given that the sides of these line segments from this corner here and corner here. So I actually labeled these vertexes over here. I'll just call this A. I'm going to call this over here B. Then what I'm going to do now is I'm actually going to start from the radius, the midpoint, and then draw the radius from over here. So it actually connects from this point over here halfway. So right here, we'll call this C. Then I'm going to do the same thing from over here, draw a line straight down. So this is going to be, I'll just call the center, the midpoint over here, D. Then we don't really need much for here. So I'm actually going to draw a diagonal line connecting from the midpoint and then all the way up to the corner of the square. So just like so. Then with this, I'm also put in a radius or vertex E over here. And so this actually forms a 45-degree angle over here as this is a square from the midpoint and then all the way up to the corner as it forms from over here. So we know that we can actually call this variable from this length the line segment CDR. And so that also has to imply from over here to here. Also put one more vertex over here, so F, then that means the length from the radius over here, this is also going to be R as well. So I'm just yammering too much about this whole construction, but I think we have everything we need in order to help find this area that we want to show for. So we see the line segment AF. So in other words, the line segment AF, we see that this is actually rewritten as the same thing as line segment EB, and then divided by 2, which is equal to the square root of 2. As you see that we can actually calculate this from the whole Pythagorean theorem. I think another thing to write down as well is we know that the line segment CD, which we said that's R, then we also know that that's the same thing as the length for AC as well. Then we know that the line segment AD, again, by applying Pythagorean theorem as well, this is the same thing that's going to equal R times the square root of 2. Then AD is going to equal, well, in other words, that means that the line segment AD is divided up with R, and then we know that we said that AF is equal to the square root of 2. So in other words, that's the same thing as R plus the square root of 2. Then we actually just solve everything out for R. So R is, in other words, actually going to equal to the square root of 2 divided by square root of 2, subtract 1. After, performing all that algebra, then we can actually simplify this out even further to say that this is the same thing as 2 plus the square root of 2. And so with this, now we actually want to find the area of this little sector over here, because the strategy is that what we're going to do is we're actually going to add the area of the sector, over here that's being subtracted from this whole half triangle over here, ADC. And then we're actually going to subtract it with this piece of the triangle over here, and then subtract it with this area of the sector over here in order to help get this little shaded area that we want. So we know that area of a sector is equal to pi r squared, and then we multiply this from some theta divided by 360 degrees. We said that the 45 degrees form over here, so we can actually calculate this area over here easily to say that. So I'll fill in, so this is going to be 45 degrees over here. So in other words, after putting all this out, so we have pi then multiplied by 2 plus the square root of 2 square times 45 degrees divided by 360 degrees, then this is going to equal to pi multiplied by 6 plus 4 times the square root of 2 and then divided by 8. And so okay, so that's nice. And so now the triangle of ABF, so triangle ABF, We know that this is base times height. We already figure out what that height is. So if we look at it this way, from the 90 degree where that base forms over here, the height is, we just found that AF is the square root of 2. So this is the square root of 2, then squared divided by 2, which this is just equal to 1. So we basically just have everything we need. So now to find this area over here, so now what I'm going to do is I'm actually going to take the whole triangle area ADC. So now that triangle ADC is, of course, we found that this is 2 plus the square root of 2, so 2 plus the square root of 2 squared divided by 2, that's actually 3 plus 2 times the square root of 2. And with that, so now that we have everything we need, so let's actually take the subtraction of everything. So this area is going to equal to 3 plus the square root of 2, or 2 times the square root of 2. Then we subtract this with the area of the triangle over here, ABF over here, which we said that this is 1. Then we subtract from the sector that we'd actually just calculate the area of, which that can be simplified to actually that's 3 plus 2 times the square root of 2, and then all that being divided by 4. Then if we actually simplify all this out, then we have 2 plus 2 times the square root of 2, then minus 3 pi over 4, and then subtract pi times square root of 2, and then divided by 2. And with that, that's actually the area of this tiny area over here that we actually wanted to calculate this the entire time, just like that. So yeah, that's pretty cool if you ask me.